हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। और कैसे हैं आप सब लोग? कैसी चल रही है आपकी तैयारी नीट एग्जाम की? और अब तो आप लोगों के बोर्ड एग्जाम्स भी आ रहे हैं, जो बच्चे हमारे बोर्ड वाले हैं और नीट की तैयारी भी साथ साथ में कर रहे हैं। तो बच्चों, ये ऑडियो बुक्स आप लोगों की बहुत हेल्प करने वाली हैं, आप लोगों के क्विक रिवीजन में, आप लोगों के थॉरो रिवीजन में। बिलीव मी, आप इसको सुन करके देखिए, आप लोगों को रियलाइज़ होगा कि हाँ, एनसीईआरटी को रिवाइज करना इतना भी इजी है। पहले मुझे भी नहीं लगता था कि ये ऑडियो बुक के थ्रू हम इतना इजीली रिवाइज कर सकते हैं, बट एक्चुअल में जब मैंने इन्हें सुना तो मुझे भी रियलाइज़ हुआ कि नहीं, हाँ, ये एक्चुअल में बच्चों के लिए बहुत 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 हेल्पफुल है। और यही वजह है कि मैं आप लोगों को हर एक सब्जेक्ट की ऑडियो बुक्स प्रोवाइड कर रही हूँ। आप लोगों की फिजिक्स की ऑडियो बुक मैं आज आप लोगों के साथ में शेयर करने वाली हूँ। कोशिश है कि पूरा चैप्टर एक वीडियो में कंप्लीट हो जाए, एक ही ऑडियो बुक आपको उसकी मिले। इसके साथ साथ ही अभी पैरेलल जो चल रही है हमारी, वो है बायोलॉजी की एनसीईआरटी ऑडियो बुक इन हिंदी। इंग्लिश वाली मैंने पहले ही अपलोड कर दी है, एंड केमिस्ट्री की भी आप लोगों की पूरी कंप्लीट अपलोडेड है। तो आप लोग प्लेलिस्ट चाहिए, देखिए, चेक करिए। साथ ही साथ में आप लोग मेरे 1 मिनट वीडियोस देख सकते हैं। जो 1 मिनट बायोलॉजी के वीडियोस हैं, उसमें मैंने 1 मिनट में पूरे कॉन्सेप्ट को एक्सप्लेन किया है, और मैं उन टॉपिक्स को पहले कंप्लीट कर रही हूँ जिनसे नीट में क्वेश्चंस बार बार पूछे जाते हैं, या फिर जो आपके बोर्ड एग्जाम्स के लिए ज़्यादा इंपॉर्टेंट है। तो उनको ज़रूर मिस मत करिएगा, अपने दोस्तों के साथ भी ज़रूर शेयर करिएगा। और हाँ, सबसे ज़रूरी बात, अगर ये ऑडियो बुक्स आपकी हेल्प कर रही हैं, आप लोग इतने अच्छे अच्छे कमेंट्स कर रहे हैं, इतने प्यार दे रहे हैं मेरे वीडियोज़ को, तो इसका मतलब कि आप इसे सुनते भी हैं। तो प्लीज़ चैनल को आप सब्सक्राइब कर लीजिए, और अगर आपको लगे कि ये हाँ हेल्पफुल है तो इसे लाइक भी ज़रूर करिएगा। अब ज़्यादा बातें नहीं करते और जल्दी से शुरू करते हैं चैप्टर 13, न्यूक्लियाई। 13.1 Introduction. In the previous chapter we have learned that in every atom the positive charge and mass are densely concentrated at the center of the atom, forming its nucleus. The overall dimensions of a nucleus are much smaller than those of an atom. Experiments on a scattering of alpha particles demonstrated that the radius of a nucleus was smaller than the radius of an atom by a factor of about 10 to the power 4. This means the volume of a nucleus is about 10 to the power minus 12 times the volume of the atom. In other words, an atom is almost empty. If an atom is enlarged to the size of a classroom, the nucleus would be the size of pinhead. Nevertheless, the nucleus contains the more than 99.9% of the mass of an atom. Does the nucleus have a structure just as the atom does? If so, what are the constituents of the nucleus? How are these held together? In this chapter, we shall look for answers to such questions. We shall discuss various properties of nuclei such as their size, mass and stability, and also associated nuclear phenomena such as radioactivity, fission and fusion. 13.2 Atomic masses and composition of nucleus. The mass of an atom is very small compared to a kilogram. For example, the mass of a carbon atom 12C is 1.992647 into 10 to the power minus 26 kilogram. Kilogram is not a very convenient unit to measure such small quantities. Therefore, a different mass unit is used for expressing atomic masses. This unit is the atomic mass unit, defined as 1/12 of the mass of the carbon atom. According to this definition, 1 Dalton is equals to mass of 1/12C atom upon 12. So here is the value is 1.660539 into 10 to the power minus 27 kilogram. The atomic masses of various elements expressed in atomic mass unit are close to being integral multiples of the mass of a hydrogen atom. There are, however, many striking exceptions to this rule. For example, the atomic mass of a chlorine atom is 35.46 Dalton. Accurate measurement of atomic masses is carried out with a mass spectrometer. The measurement of atomic masses reveals the existence of different types of atoms of the same element, which exhibit the same chemical properties but differ in mass. Such atomic species of the same element differing in mass are called isotopes. Isotope means the same place, that is, they occur in the same place in the periodic table of elements. It was found that practically every element consists of a mixture of several isotopes. The relative abundance of different isotopes differ from element to element. Chlorine, for example, has 2 isotopes having masses 34.98 Dalton and 36.98 Dalton, which are nearly integral multiplies of the mass of a hydrogen atom. The relative abundances of these isotopes are 75.4 and 24.6% respectively. Thus, the average mass of a chlorine atom is obtained by the weighted average of the masses of the 2 isotopes, which works out to be, and the final value is 35.47 Dalton, which agrees with the atomic mass of chlorine. Even the lightest element hydrogen has three isotopes having masses 1.0078 Dalton, 2.0141 Dalton and 3.0160 Dalton. The nucleus of the lightest atom of hydrogen, which has a relative abundance of 99.985%, is called the proton. The mass of a proton is 1.67262 into 10 to the power minus 27 kg. This is equal to the mass of hydrogen atom, that is 1.00783 Dalton, minus the mass of a single electron, that is 0.00055 Dalton. The other two isotopes of hydrogens are called deuterium and tritium. Tritium nuclei, being unstable, do not occur naturally and are produced artificially in laboratories. The positive charge in the nucleus is that of the protons. A proton carries 1 unit of fundamental charge and is stable. It was earlier thought that the nucleus may contain electrons, but this was ruled out later using argument based on quantum theory. All the electrons of an atom are outside the nucleus. We know that the number of these electrons outside the nucleus of the atom is Z, the atomic number. The total charge of the atomic electrons is thus minus Ze. And since the atom is neutral, the charge of the nucleus is plus Ze or positive Ze. The number of protons in the nucleus of the atom is therefore exactly Z, the atomic number. Discovery of neutron. Since the nuclei of deuterium and tritium are isotopes of hydrogen, they must contain only one proton each, but the masses of the nuclei of hydrogen, deuterium and tritium are in the ratio of 1:2:3. Therefore, the nuclei of deuterium and tritium must contain, in addition to a proton, some neutral matter. The amount of neutral matter present in the nuclei of these isotopes, expressed in units of mass of a proton, is approximately equal to 1 and 2 respectively. This fact indicates that the nuclei of atom contains, in addition to protons, neutral matter in multiplies of a basic unit. This hypothesis was verified in 1932 by James Chadwick, who observed emission of neutral radiation when beryllium nuclei were bombarded with alpha particles. Alpha particles are helium nuclei, to be discussed in later section. It was found that this neutral radiation could knock out protons from light nuclei such as those of helium, carbon and nitrogen. The only neutral radiation known at that time was photons, that is electromagnetic radiation. Application of the principle of conservation of energy and momentum showed that if the neutral radiation consisted of photons, the energy of photons would have to be much higher than this is available from bombardment of beryllium nuclei with alpha particles. The clue to this puzzle, which Chadwick satisfactorily solved, was to assume that the neutral radiation consisted of new type of neutral particles called neutrons. From conservation of energy and momentum, he was able to determine the mass of new particle as very nearly the same as mass of proton. The mass of a neutron is now known to a high degree of accuracy. It is Mn is equals to 1.00866 Dalton is equals to 1.6749 into 10 to the power minus 27 kg. Chadwick was awarded the 1935 Nobel Prize in Physics for his discovery of the neutron. A free neutron, unlike a free proton, is unstable. It decays into a proton, an electron and an antineutrino, another elementary particle, and has a mean life of about 1/1000. It is, however, stable inside the nucleus. The composition of a nucleus can now be described using the following terms and symbols. Z is equals to atomic number, that is number of protons. N is equals to neutron number, number of neutrons, and A is the mass number, Z plus N, total number of protons and neutrons. One also uses the term nucleon for a proton or a neutron. Thus, the number of nucleon in an atom is its mass number A. Nuclear species or nucleides are shown by the notation AXZ, where X is the chemical symbol of the species. For example, the nucleus of gold is denoted by 19779 AU. It contains 197 nucleons, of which 79 are protons and the rest 118 are neutrons. The composition of isotopes of an element can now be readily explained. The nuclei of isotopes of a given element contain the same number of protons but differ from each other in their number of neutrons. Deuterium 1H2, which is an isotope of hydrogen, contains one proton and one neutron. Its other isotope tritium 1H3 contains 1 proton and 2 neutrons. The element gold has 32 isotopes ranging from A is equals to 173 to A204. We have already mentioned that chemical properties of elements depend on their electronic structure. As the atoms of isotopes have identical electronic structure, they have identical chemical behavior and are placed in the same location in the periodic table. All nucleides with same mass number A are called isobars. For example, the nucleides 1H3 and 2He3 are isobars. Nucleides with same neutron number N but different atomic number Z, for example 80Hg 198 and 79Au 197, are called isotones. 13.3 Size of the nucleus. As we have seen in chapter 12, Rutherford was the pioneer who postulated and established the existence of the atomic nucleus. At Rutherford's suggestion, Geiger and Marsden performed their classic experiment on the scattering of alpha particles from thin gold foils. Their experiments revealed that the distance of closest approach to a gold nucleus of an alpha particle of kinetic energy 5.5 megawatt is about 4.0 into 10 to the power minus 14 m. The scattering of alpha particle by the gold sheet could be understood by Rutherford by assuming that the Coulomb repulsive force was solely responsible for scattering. Since the positive charge is confined to the nucleus, the actual size of the nucleus has to be less than 4.0 into 10 to the power minus 14 m. If we use alpha particles of higher energies than 5.5 MeV, the distance of closest approach to the gold nucleus will be smaller, and at same point the scattering will begin to be affected by the short-range nuclear forces and differ from Rutherford's calculations. Rutherford's calculations are based on pure Coulomb repulsion between the positive charges of the alpha particle and the gold nucleus. From the distance at which deviations set in, nuclear sizes can be inferred. By performing scattering experiments in which fast electrons instead of alpha particles are projectiles that bombarded targets made up of various elements, the sizes of the nuclei of various elements have been accurately measured. It has been found that a nucleus of mass number A has a radius r is equals to r naught a to the power 1 by 3, where r naught is equals to 1.2 into 10 to the power minus 15 meter, and that is 10 to the power minus 15 meter, 1 femtometer. This means the volume of the nucleus, which is proportional to r to the power 3, is proportional to A. Thus, the density of nucleus is constant independent of A for all nuclei. Different nuclei are like a drop of liquid of constant density. The density of nuclear matter is approximately 2.3 into 10 to the power 17 kilogram per meter cube. This density is very large compared to ordinary matter, say water, which is 10 to the power 3 kilogram per meter cube. This is understandable as we have already seen that most of the atom is empty. Ordinary matter consisting of atoms has a large amount of empty space. 13.4 Mass energy and nuclear binding energy. 13.4.1 Mass energy. Einstein showed from his theory of special relativity that it is necessary to treat mass as another form of energy. Before the advent of this theory of special relativity, it was presumed that mass and energy were conserved separately in a reaction. However, Einstein showed that mass is another form of energy and one can convert mass energy into other forms of energy, say kinetic energy and vice versa. Einstein gave the famous mass energy equivalence relation E is equals to mc square. Here the energy equivalent of mass m is related by the above equation, and c is the velocity of light in vacuum and is approximately equal to 3 into 10 to the power 8 meter per second. Experimental verification of the Einstein mass energy relation has been achieved in the study of nuclear reactions amongst nucleons, nuclei, electrons and other more recently discovered particles. In a reaction, the conservation law of energy states that the initial energy and the final energy are equal provided the energy associated with mass is also included. This concept is important in understanding nuclear masses and the interaction of nuclei with one another. They form the subject matter of the next few sections. 13.4.2 Nuclear binding energy. In section 13.2, we have seen that the nucleus is made up of neutrons and protons. Therefore, it may be expected that the mass of nucleus is equal to the total mass of its individual protons and neutrons. However, the nuclear mass m is found to be always less than this. For example, let us consider 8O16, a nucleus which has 8 neutrons and 8 protons. We have mass of 8 neutrons 8 into 1.00866 Dalton, mass of 8 protons 8 into 1.00727 Dalton, mass of 8 electrons 8 into 0.00055 Dalton. Therefore, the expected mass of 8O16 nucleus is 16.127444 Dalton. The atomic mass of 8O16 found from mass spectroscopy experiment is seen to be 15.99493 Dalton. Subtracting the mass of 8 electrons from this, we get the experimental mass of 8O16 nucleus to be 15.99053 Dalton. Thus, we find that the mass of 8O16 nucleus is less than the total mass of its constituents by 0.13691 Dalton. The difference in mass of a nucleus and its constituents delta m is called the mass defect and is given by delta m is equals to zmp plus a minus z into mn the whole minus m. What is the meaning of the mass defect? It is here the Einstein's equivalence of mass and energy plays a role. Since the mass of the oxygen nucleus is less than the sum of the masses of its constituents, the equivalent energy of oxygen nucleus is less than that of sum of the equivalent energies of its constituents. If one wants to break the oxygen nucleus into 8 protons and 8 neutrons, the extra energy delta mc square has to be supplied. This energy required EB is related to the mass defect by EB is equals to delta mc square. If a certain number of neutrons and protons are brought together to form a nucleus of a certain charge and mass, an energy EB will be released in the process. The energy EB is called the binding energy of the nucleus. If we separate a nucleus into its nucleons, we would have to supply a total energy equal to EB to those particles. Although we cannot tear apart a nucleus in this way, the nuclear binding energy is still a convenient measure of how well a nucleus is held together. A more useful measure of the binding between the constituents of the nucleus is binding energy per nucleon, EBN, which is the ratio of binding energy EB of a nucleus to the number of nucleons A in that nucleus. EBN is equals to EB upon A. We can think of binding energy per nucleon as the average energy per nucleon needed to separate a nucleus into its individual nucleons. Figure 13.1 is a plot of the binding energy per nucleon, EBN versus the mass number A for a large number of nuclei. We notice the following main features of the plot. Number 1. The binding energy per nucleon EBN is practically constant, that is practically independent of the atomic number of nuclei of middle mass number. The curve has a maximum of about 8.75 MeV for A is equals to 56 and has a value of 7.6 MeV for A is equals to 238. EBN is lower for both light nuclei, that is A is less than 30 and heavy nuclei is greater than 170. We can draw some conclusions from these two observations. Number 1. The force is attractive and sufficiently strong to produce a binding energy of a few MeV per nucleon. Number 2. The constancy of the binding energy is the range 30 greater than 30 less than A is less than 170 is consequence of the fact that the nuclear force is short ranged. Consider a particular nucleon inside a sufficiently large nucleus. It will be under the influence of only some of its neighbors which come within the range of the nuclear force. If any other nucleon is at a distance more than the range of a nuclear force from the particular nucleon, it will have no influence on the binding energy of the nucleon under consideration. If a nucleon can have a maximum of P neighbors within the range of a nuclear force, its binding energy would be proportional to P. Let the binding energy of the nucleus be pk, where k is the constant having the dimensions of energy. If we increase A by adding nucleons, they will not change the binding energy of a nucleon inside. Since most of the nucleons in a large nucleus reside inside it and not on the surface, the change in binding energy per nucleon would be small. The binding energy per nucleon is a constant and is approximately equal to pk. The property of that a given nucleon influences only nucleons close to its, also referred to as a saturation property of the nuclear force. Number 3. A very heavy nucleus, say A is equals to 240, has lower binding energy per nucleon compared to that of nucleus with A is equals to 120. Thus, if a nucleus is 240 breaks into 2A is equals to 120 nuclei, nucleons get more tightly bound. This implies energy would be released in the process. It has very important implications for energy production through fission, to be discussed later in section 13.7.1. Fourth, consider two very light nuclei, A less than or equal to 10. Joining to form a heavier nucleus, the binding energy per nucleon of the fused heavier nuclei is more than the binding energy per nucleon of the lighter nuclei. This means that the final system is more tightly bound than the initial system. Again, energy would be released in such a process of the fusion. This is the energy source of Sun, to be discussed later in section 13.7.3. 13.5 Nuclear force. The force that determines the motion of atomic electrons is the familiar Coulomb force. In section 13.4, we have seen that for average mass nuclei, the binding energy per nucleon is approximately 8 MeV, which is much larger than the binding energy in atoms. Therefore, to bind a nucleus together, there must be a strong attractive force of a totally different kind. It must be strong enough to overcome the repulsion between the positively charged protons and to bind both protons and neutrons into a tiny nuclear volume. We have already seen that the consistency of binding energy per nucleon can be understood in terms of its short range. Many features of the nuclear binding force are summarized below. These are obtained from a variety of experiments carried out during 1930 to 1950. Number 1. The nuclear force is much stronger than the Coulomb force acting between charges or the gravitational forces between masses. The nuclear binding force has to dominate over the Coulomb repulsive force between protons inside the nucleus. This happens only because the nuclear force is much stronger than the Coulomb force. The gravitational force is much weaker than even Coulomb force. Number 2. The nuclear force between two nucleons falls rapidly to zero as their distance is more than a few femtometers. This leads to saturation of forces in a medium or a large-sized nucleus, which is the reason for the constancy of the binding energy per nucleon. A rough plot of the potential energy between two nucleons as a function of distance is shown in the figure 13.2. The potential energy is a minimum at a distance r0 or r0 of about 0.8 femtometer. This means that the force is attractive but distance is larger than 0.8 femtometer and repulsive if they are separated by distances less than 0.8 femtometer. Number 3. The nuclear force between neutron-neutron, proton-neutron and proton-proton is approximately the same. The nuclear force does not depend on the electric charge. Unlike Coulomb's law or the Newton's law of gravitation, there is no simple mathematical form of the nuclear force. 13.6 Radioactivity. A.H. Becquerel discovered radioactivity in 1896 purely by accident while studying the fluorescence and phosphorescence of compounds irradiated with visible light. Becquerel observed an interesting phenomenon. After illuminating some pieces of uranium potassium sulfate with visible light, he wrapped them in black paper and separated the package from a photographic plate by a piece of silver. When after several hours of exposure, the photographic plate was developed, it showed blackening due to something that must have been emitted by the compound and was able to penetrate both black paper and the silver. Experiments performed subsequently showed that radioactivity was a nuclear phenomena in which an unstable nucleus undergoes a decay. This is referred to as radioactive decay. 3 types of radioactive decay occur in nature. Number 1. Alpha decay, in which a helium nucleus 2He4 is emitted. Number 2. Beta decay, in which electrons or positrons, that is particles with the same mass as electrons but with a charge exactly opposite that of electrons, are emitted. Number 3. Gamma decay, in which high energy, that is hundreds of keV or more, photons are emitted. Each of these decay will be considered in subsequent subsections. 13.6.1 Law of radioactive decay. 13.6.1 Law of radioactive decay. In any radioactive sample which undergoes alpha, beta or gamma decay, it is found that the number of nuclei undergoing the decay per unit time is proportional to the total number of nuclei in the sample. If n is the number of nuclei in the sample and delta n undergo decay in the delta t time, then delta n upon delta t is directly proportional to n, or delta n upon delta t is equals to lambda n, where lambda is called the radioactive decay constant or disintegration constant. The change in the number of nuclei in the sample is dn is equals to minus delta n in the time delta t. The rate of change of n is in the limit delta t to 0. dn upon dt is equals to minus lambda n. Delta n is the number of nuclei that decay and hence is always positive. Dn is the change in n, which may have either sign. Here it's is negative because out of original n nuclei, delta n have decayed, leaving n minus delta n nuclei. Now here you can see all the calculation, all the reactions, equations. Note, for example, the light bulbs follow no such exponential decay law. If we test 1000 bulbs for their lifetime span before they burn out or fuse, we expect that they will decay, that is burn out, at more or less the same time. The decay of radionuclides follow quite a different law, the law of radioactive decay represented by equation 13.14. Now here the total decay rate R of a sample is the number of nuclei disintegrating per unit time. Suppose in a time interval dt, the decay count measured is delta n, and then dn is equals to minus delta n. And here you can see again the complete thing. The decay rate of a sample rather than the number of radioactive nuclei is a more direct experimentally measurable quantity and is given a specific name activity. The SI unit for activity is becquerel, named after the discovery of radioactivity, Henry Becquerel. 1 becquerel is simply equal to 1 disintegration or decay per second. There is also another unit named Curie that is widely used and is related to the SI unit as 1 Curie is equals to 3.7 into 10 to the power 10 becquerel. Different radionuclides differ greatly in their rate of decay. A common way to characterize this feature is through the notion of half-life. Half-life of a radionuclide, denoted by T half, is the time it takes for the sample that has initially say and not radionuclide to reduce and not upon 2. And now here you can see the value, that is a 0.693 upon lambda. Clearly, if a naught reduces to half its value in time t half, a naught will also reduce to half its value in the same time according to equation 13.16. Another related measure is the average or mean life tau. This again can be obtained from equation 13.14. The number of nuclei which decay in the time interval t to t plus delta t is r t delta t. Each of them has lived for time t. Thus the total life of all these nuclei would be t lambda n naught e to the power minus lambda t delta t. It is clear that some nuclei may live for a short time while others may live longer. Therefore, to obtain the mean life, we have to sum or integrate this expression over all times 0 to infinity and divide by the total number n naught of nuclei at t is equals to 0 thus. Now here is something for Marie Curie. Born in Poland, she is recognized both as a physicist and as a chemist. The discovery of radioactivity by Henry Becquerel in 1896 inspired Marie and her husband Pierre Curie in their researches and analyses, which led to the isolation of radium and polonium elements, which was the first person to be awarded 2 Nobel Prizes for physics in 1903 and for chemistry in 1911. Radioactive elements, tritium, plutonium, which are short-lived, that is, have half-lives much less than the age of universe, have obviously decayed long ago and are not found in nature. They can, however, be produced artificially in nuclear reactions. 13.6.2 Alpha decay. A well-known example of alpha decay is the decay of uranium-92, uranium-238 to thorium-90, thorium-234 with the emission of a helium nucleus 2He4. Here you can see the reaction. In alpha decay, the mass number of the product nucleus, daughter nucleus, is 4 less than that of decaying nucleus, parent nucleus, while the atomic number decreases by 2 in general alpha decay of a parent nucleus. ZXA results in a daughter nucleus. This. Here you can see the next 13.20 equation. From Einstein mass energy equivalence relation and energy conservation, it is clear that this spontaneous decay is possible only when the total mass of the decay product is less than the mass of the initial nucleus. This difference in mass appears as kinetic energy of the products. By referring to a table of nuclear masses, one can check that total mass 90 thorium 234 and 2He4 is indeed less than that of 92 uranium 238. The disintegration energy or Q value of a nuclear reaction is the difference between the initial mass energy and the total mass energy of the decay products for alpha decay. So here is the Q is equals to mx minus my minus mhe into c square. Q is also the net kinetic energy gained in the process, or if the initial nucleus X is at rest, the kinetic energy of the products, clearly Q is greater than 0 for exothermic processes such as alpha decay. Examples: 13.6.3 beta decay. In beta decay, a nucleus spontaneously emits an electron or a positron. A common example of beta decay is, here is a reaction and here is the another reaction, and the decays are governed by the equation 13.14 and 13.15, so that one can never predict which nucleus will undergo decay, but one can characterize the decay by a half-life T1/2. For example, T half for the decays above is respectively 14.3 D and 2.6 Y. The emission of electron in beta decay is accompanied by the emission of anti-neutrino in beta positive decay. Instead, a neutrino is generated. Neutrinos are neutral particles with very small, possibly even zero, mass compared to electrons. They have only weak interaction with other particles. They are therefore very difficult to detect since they can penetrate large quantity of matter, even Earth, without any interaction. In both beta negative and beta positive decay, the mass number A remains unchanged in beta decay. The atomic number Z of the nucleus goes up by 1, while in beta positive decay Z goes down by 1. The basic nuclear process underlying beta decay is the conversion of neutron to proton. Here you can see. Note that while a free neutron decay to proton, the decay of proton to neutron, equation 13.25, here it is possible only inside the nucleus since proton has a smaller mass than neutron. 13.6.4 Gamma decay. Like an atom, a nucleus also has discrete energy levels, the ground state and excited states. The scale of energy is, however, very different. Atomic energy level spacings are of the order of eV, electron volt, while the difference in nuclear energy levels is of the order of MeV. And when a nucleus in an excited state spontaneously decays to its ground or to a lower energy state, a photon is emitted with energy equal to the difference into the two energy levels of the nucleus. This is so-called gamma decay. The energy corresponds to radiation of extremely short wavelength, shorter than the hard X-ray region. Typically, a gamma ray is emitted when alpha or beta decay results in a daughter nucleus in an excited state. This then returns to the ground state by a single photon transition or successive transitions involving more than one photon. A familiar example is the successive emission of gamma rays of energies 1.17 MeV and 1.33 MeV from the de-excitation of 28 Nickel 60 nuclei formed from beta decay of 27 cobalt 60. 13.7 Nuclear energy. The curve of binding energy per nucleon, EBN, given in figure 13.1 has a long flat middle region between A is equals to 30 and A is equals to 170. In this region, the binding energy per nucleon is nearly constant, 8 MeV around, and for the lighter nuclei region, A is less than 30, and for the heavier nuclei region, A is greater than 170, the binding energy per nucleon is less than 8 MeV, as we have noted earlier. Now, the greater the binding energy, the less is the total mass of a bound system such as nucleus. Consequently, if nuclei with less total binding energy transform to nuclei with greater binding energy, there will be a net energy release. This is what happens when a heavy nucleus decays into two or more intermediate mass fragments, fission, or when light nuclei fuse into a heavier nucleus, that is fusion. Exothermic chemical reactions underlie conventional energy sources such as a coal or petroleum. Here the energies involved are in the range of electron volts. On the other hand, in a nuclear reaction, the energy release is of the order of megavolt. Thus, for the same quantity of matter, nuclear sources produce 1,000,000 times more energy than a chemical source. Fission of 1 kg of uranium, for example, generates 10 to the power 14 joule of energy. Compare it with burning of 1 kg of coal, that gives 10 to the power 7 joule. 13.7.1 Fission. New possibilities emerge when we go beyond natural radioactive decays and study nuclear reactions by bombarding nuclei with other nuclear particles such as proton, neutron, alpha particle, etc. A most important neutron-induced nuclear reaction is fission. An example of fission is when a uranium isotope 92 uranium-235 bombarded with a neutron breaks into two intermediate mass nuclear fragments. Here is the reaction. The same reaction can produce other pairs of intermediate mass fragments. The remaining two reactions. The fragment products of are radioactive nuclei. They emit beta particles in succession to achieve stable end products. The energy released, the Q value in the fission reaction of nuclei like uranium is of the order of 200 per fissioning nucleus. This is estimated as follows. So here let us take a nucleus of A240 breaking into the two fragments each of A120. Then you can see EBN for A240 nucleus is about 7.6 MeV and for the 2A120 fragment nuclei is about 8.5 MeV. Gain in binding energy for nucleon is about 0.9 MeV. Hence the total gain in binding energy is 240 into 0.9 or 216 MeV. The disintegration energy in fission events first appears as the kinetic energy of the fragments and neutrons. Eventually it is transferred to the surrounding matter appearing as heat. The source of energy in nuclear reactors which produce electricity is nuclear fission. The enormous energy released in an atom bomb comes from uncontrolled nuclear fission. We discuss some details in the next section how a nuclear reactor functions. 13.7.2 Nuclear reactor. Notice one fact of great importance in the fission reactions given in equations 13.26 to 13.28. There is a release of extra neutron in the fission process. Averagely 2.5 neutrons are released per fission of uranium nucleus. It is a fraction since in some fission events 2 neutrons are produced, in some 3, etc. The extra neutrons in turn can initiate fission process by producing still more neutrons and so on. This leads to the possibility of a chain reaction as was first suggested by Enrico Fermi. If the chain reaction is controlled by suitably, we can get a steady energy output. This is what happens in nuclear reactor. If the chain reaction is uncontrolled, it leads to explosive energy output as in a nuclear bomb. There is, however, a hurdle in sustaining a chain reaction as described here. It is known experimentally that slow neutrons, thermal neutrons, are much more likely to cause fission in 92 uranium-235 than fast neutrons. Also, fast neutrons liberated in fission would escape instead of causing another fission reaction. The average energy of a neutron produced in fission of 92 uranium-235 is 2 MeV. These neutrons, unless slowed down, will escape from the reactor without interacting with the uranium nuclei, unless a very large amount of fissionable material is used for sustaining the chain reaction. What one needs to do is to slow down the fast neutrons by elastic scattering with light nuclei. In fact, Chadwick experiment showed that in an elastic collision with hydrogen, the neutron almost comes to rest and proton carries away the energy. This is the same situation as when a marble hits head on identical marble at rest. So therefore, in reactors, light nuclei called moderators are provided along with the fissionable nuclei for slowing down fast neutrons. The moderators commonly used are water, heavy water, D2O and graphite. The Apsara reactor at the Bhabha Atomic Research Institute, Barkatis, Mumbai uses water as moderator. The other Indian reactors which are used for power production use heavy water as moderator. Because of the use of moderator, it is possible that the ratio K of number of fission produced by a given generation of neutrons to the number of fission of the preceding generation may be greater than 1. This ratio is called the multiplication factor. It is the measure of the growth rate of neutrons in the reactor. For K is equals to 1, the operation of the reactor is said to be critical, which is what we wish it to be for a steady power operation. If K becomes greater than 1, the reaction rate and the reactor power increases exponentially. Unless the factor K is brought down very close to unity, the reactor will become supercritical and can even explode. The explosion of Chernobyl reactor in Ukraine in 1986 is a sad reminder that accidents in a nuclear reactor can be catastrophic. The reaction rate is controlled through control rods made out of neutron-absorbing materials such as cadmium. In addition to control rods, reactors are provided with safety rods which, when required, can be inserted into the reactor, and K can be reduced rapidly to less than unity. The more abundant isotope 92 uranium-238 in naturally occurring uranium is non-fissionable. When it captures a neutron, it produces the highly radioactive plutonium through these reactions. Here you can see the reactions. Plutonium undergoes fission with slow neutrons. Figure 13.5 shows the schematic diagram of nuclear reactor based on thermal neutron fission. The core of the reactor is the site of nuclear fission. It contains the fuel elements in suitably fabricated form. The fuel may be, say, enriched uranium, that is that has greater abundance of uranium than naturally occurring uranium. The core contains a moderator to slow down the neutrons. The core is surrounded by a reflector to reduce leakage. The energy released in fission is continuously removed by a suitable coolant. The contaminant vessel prevents the escape of radioactive fission products. The whole assembly is shielded to check harmful radiation from coming out. The reactor can be shut down by means of rods made of, for example, cadmium that have high absorption of neutrons. The coolant transfer heat to a working fluid which in turn may produce steam. The steam derives turbines and generates electricity. Like any power reactor, nuclear reactors generate considerable waste products, but nuclear waste need special care for treatment since they are radioactive and hazardous. Elaborate safety measures both for reactor operation as well as handling and reprocessing the spent fuel are required. These safety measures are a distinguishing feature of the Indian Atomic Energy Program. An appropriate plan is being evolved to study the possibility of converting radioactive waste into less active and short-lived material. Here is one information I have to read, that is about the India's atomic energy program. The atomic energy program in India was launched around the time of independence under the leadership of Homi J. Bhabha, 1909 to 1966. An early historic achievement was the design and construction of the first nuclear reactor in India named Apsara, which went critical on 4th August 1956. It used enriched uranium as fuel and water as moderator. Following this was another notable landmark, the construction of CERT, Canada, India, Research, US reactor in 1960. This 40 megawatt reactor used natural uranium as fuel and heavy water as moderator. Apsara and CERT spurred research in a wide range of areas of basic and applied nuclear science. An important milestone in the first 2 decades of the program was the indigenous design and constructions of the plutonium plant at Trombay, which ushers in the technology of fuel reprocessing in India. Research reactors that have been subsequently commissioned included Zarlina, Purnima, 1st, 2nd and 3rd, Dhruva and Kamini. Kamini is the country's first large research reactor that uses U-233 as fuel. As the name suggests, the primary objective of research reactor is not generation of power but to provide a facility for research on different aspects of nuclear science and technology. Research reactors are also an excellent source for production of variety radioactive isotopes that find application in diverse fields, industry, medicine and agriculture. The main objectives of Indian Atomic Energy Program are to provide safe and reliable electric power for the country's social and economic progress and to be self-reliant in all aspects of nuclear technology. Exploration of atomic minerals in India undertaken since the early 50s has indicated that India has limited reserves of uranium but fairly abundant reserves of thorium. Accordingly, our country has adopted a 3-stage strategy of nuclear power generation. The first stage involves the use of natural uranium as a fuel with heavy water as moderator. The plutonium-239 obtained from reprocessing of the discharged fuel from the reactors then serves as a fuel for the second stage, the fast breeder reactors. They are also called because they use fast neutrons for sustaining the chain reaction, hence no moderator is needed. And besides generating power, also breed more fissile species plutonium than they consume. The third stage, more significantly in the long term, involves using fast breeder reactors to produce fissile uranium-233 from thorium-232 and to build power reactors based on them. India is currently well into second stage of the program and considerable work has also been done on the third, the thorium utilization stage. The country has mastered the complex technologies of mineral exploration and mining, fuel fabrication, heavy water production, reactor design, constructions and operation, fuel reprocessing, etc. Pressurized heavy water reactors (PHWRs) built at different sites in the country, mark the accomplishment of the first stage of the program. India is now more than self-sufficient in heavy water production. Elaborate safety measures both in the design and operation of reactors as also adhering the stringent standards of radiological protection are the hallmark of the Indian atomic energy program. 13.7.3 Nuclear fusion, energy generation in stars. When two light nuclei fuse to form a larger nucleus, energy is released. Since the larger nucleus is more tightly bound, as seen from the binding energy curve in figure 13.1. Some examples of such energy liberating nuclear fusions reactions are here. You can see all the three reactions. In the first reaction, two protons combine to form a neutron and a positron will release of 0.42 MeV energy. In reaction 13.29b, two deuterons combine to form a light isotope of helium. In reaction 13.29c, two deuterons combine to form a triton and a proton. For fusion to take place, the two nuclei must come close enough so that attractive short-range nuclear force is able to affect them. However, since they are both positively charged particles, they experience Coulomb repulsion. They therefore must have enough energy to overcome this Coulomb barrier. The height of the barrier depends on the charges and the radii of the two interacting nuclei. It can be shown, for example, that the barrier height for two proton is approximately 400 keV, kiloelectron volt, and is higher for nuclei with higher charges. We can estimate the temperature at which two protons in a proton gas averagely have enough energy to overcome the Coulomb barrier. Here you can see this. When fusion is achieved by raising the temperature of the system so that particles have enough kinetic energy to overcome the Coulomb repulsive behavior, it is called the thermonuclear fusion. Thermonuclear fusion is a source of energy output in the interior of stars. The interior of the Sun has a temperature of 1.5 into 10 to the power 7 Kelvin, which is considerably less than the estimated temperature required for fusion of particles of average energy. Clearly, fusion in the Sun involves protons whose energies are much above the average energy. The fusion reaction in the Sun is a multi-step process in which the hydrogen is burned into the helium. Thus, the fuel in the Sun is the hydrogen in its core. The proton-proton cycle by which this occurs is represented by the following sets of reaction. Here you can see all the four reactions. 1, 2, 3, 4. For the fourth reaction to occur, the first three reactions must occur twice, in which case two light helium nuclei unite to form ordinary helium nucleus. If we consider the combination, the net effect is, here is the reaction. Thus, four hydrogen atoms combine to form an 2He4 atom, helium atom, with a release of 26.7 MeV of energy. Helium is not the only element that can be synthesized in the interior of a star. As the hydrogen in the core gets depleted and becomes helium, the core starts to cool. The star begins to collapse under its own gravity, which increases the temperature of the core. If this temperature increases to about 10 to the power 8 Kelvin, fusion takes place again, this time of helium nuclei into carbon. This kind of process can generate through fusion higher and higher mass number elements. But elements more massive than those near the peak of the binding energy curve in figure 13.1 cannot be so produced. The age of the Sun is about 5 into 10 to the power 9. And it is estimated that there is enough hydrogen in the Sun to keep it going for another 5 billion years. After that, the hydrogen burning will stop and the Sun will begin to cool and will start to collapse under gravity, which will raise the core temperature. The outer envelope of the Sun will expand, turning it into the so-called red giant. In a single uranium fission, about 0.9 into 235 MeV of energy is liberated. If each nucleus is about 50 kg of 235 uranium undergoes fission, the amount of energy involved is about 4 into 10 to the power 15 joule. This energy is equivalent to about 20,000 tons of TNT, enough for a super explosion. Uncontrolled release of large nuclear energy is called an atomic explosion. On August 6, 1945, an atomic device was used in warfare for the first time. The US dropped an atom bomb on Hiroshima, Japan. The explosion was equivalent to 20,000 tons of TNT. Instantly, the radioactive products devastated 10 square kilometers of the city, which is more than 67% of the city's structure were destroyed. of the city, which had 343,000 inhabitants. Of this number of 66,000 were killed and 69,000 were injured. More than 67% of the city's structure were destroyed. High temperature conditions for fusion reaction can be created by exploding a fission bomb. Super explosions equivalent to 10 megatons of explosion power of TNT were tested in 1954. Such bombs, which involve fusion of isotopes of hydrogen, deuterium, and tritium, are called hydrogen bombs. It is estimated that a nuclear arsenal sufficient to destroy every form of life on this planet several times over is in position to be triggered by the press of a button. Such a nuclear holocaust will not only destroy the life that exists now, but its radioactive fallout will make the planet unfit for life for all times. Scenarios based on theoretical calculation predict a long nuclear winter, as the radioactive waste will hang like a cloud in the Earth's atmosphere and will absorb the sun's radiation. Controlled thermonuclear fusion. The natural thermonuclear fusion process in a star is replicated in a thermonuclear fusion device. Controlled fusion reactors, the aim is to generate steady power by heating the nuclear fuel to a temperature in the range of 10 to the power 8 Kelvin. At these temperatures, this fuel is a mixture of positive ions and electrons, plasma. The challenge is to confine the plasma, since no container can stand such a high temperature. Several countries around the world, including India, are developing techniques in this connection. If successful, fusion reactors will hopefully supply almost unlimited power to humanity. Summary. An atom has a nucleus. The nucleus is positively charged. The radius of the nucleus is smaller than the radius of an atom by a factor of 10 to the power 4. More than 99.9% mass of the atom is concentrated in the nucleus. Number 2. On the atomic scale, mass is measured in atomic mass unit. By definition, one atomic mass unit is 1/12th mass of an atom of carbon. Number 3. A nucleus contains a neutral particle called neutron. Its mass is almost the same as that of proton. Number 4. The atomic number Z is the number of protons in the atomic nucleus of an element. The mass number A is the total number of protons and neutrons in the atomic nucleus. A is equals to Z plus N. Here N denotes the number of neutrons in the nucleus. A nuclear species or a nuclide is represented as ZXA, where X is the chemical symbol of the species. Nucleides with the same atomic number Z but different neutron number N are called isotopes. Nuclides with the same A are isobars, and those with the same N are isotones. Most elements are mixtures of two or more isotopes. The atomic mass of an element is a weighted average of the masses of its isotopes and calculated in accordance to the relative abundance of the isotopes. A nucleus can be considered to be spherical in shape and assigned a radius. Electron scattering experiment allowed determination of the nuclear radius. It is found that radii of nuclei fit the formula R is equals to R naught A to the power 1 by 3. Neutrons and protons are bound in a nucleus by the short range strong nuclear force. The nuclear force does not distinguish between neutron and proton. The nuclear mass m is always less than total mass sigma m of its constituents. The difference in mass of a nucleus and its constituents is called the mass defect. Here you can see it. Using Einstein's the mass energy relation, we express this mass difference in terms of energy is EB is equals to delta mc square. The energy delta E represents the binding energy of the nucleus. In the mass number range A is equals to 30 to 170, the binding energy per nucleon is nearly constant, about 8 MeV per nucleon. 8th, energies associated with nuclear processes are about 1,000,000 times larger than chemical process. 9th, the Q value of a nuclear process is Q is equals to final kinetic energy minus initial kinetic energy. Due to conservation of mass energy, this is also Q is sum of initial masses minus sum of final masses into C square. 10th, radioactivity is the phenomena in which nuclei of a given species is transformed by giving out alpha or beta or gamma rays. X-rays are helium nuclei. Beta rays are electrons. Gamma rays are electromagnetic radiations of wavelengths shorter than X-rays. 11th, law of radioactive decay. Nt is equals to N0 e to the power minus lambda t, where lambda is the decay constant or disintegration constant. The half-life of a radionuclide is the time in which N has been reduced to 1/2 of its initial value. The mean life tau is the time at which N has been reduced to e to the power minus 1 of its initial value. Here you can see this. Energy is released when less tightly bound nuclei are transmuted into more tightly bound nuclei. In fission, a heavy nucleus like 92 uranium 235 breaks into two smaller fragments. Here you can see the reaction. 13th, the fact that more neutrons are produced in fission than are consumed gives the possibility of a chain reaction with each neutron that is produced triggering another fission. The chain reaction is uncontrolled and rapid in a nuclear bomb explosion. It is controlled and steady in a nuclear reactor. In a reactor, the value of neutron multiplication factor K is maintained at 1. In fusion, lighter nuclei combine to form a larger nucleus. Fusion of hydrogen nuclei into helium nuclei is the source of energy of all stars including our sun. और इसी के साथ में आपकी ऑडियो बुक कंप्लीट हो गई है. अब आप लोग मुझे कमेंट सेक्शन में ज़रूर बताना कि आप लोगों को कैसी लगी, क्या वाकई में इसने आपकी हेल्प रिवीजन में की या फिर नहीं की. तो आप मुझे इसको ज़रूर बताइएगा कमेंट सेक्शन में कि क्या इसमें और कुछ इम्प्रूवमेंट किया जा सकता है, और साथ ही साथ ये भी ज़रूर बताइएगा कि नेक्स्ट कौन सा चैप्टर आपको चाहिए. सो आप लोगों के बताने के बाद ही मैं इसकी दूसरी ऑडियो बुक प्रिपेयर करूँगी. एंड चलिए मिलते हैं नेक्स्ट ऑडियो बुक में अगेन. तब तक के लिए टाटा बाय बाय एवरीवन, टेक केयर, ऑल द बेस्ट, जस्ट स्टे ट्यून्ड विद मी, बाय बाय.